Awesome. Thanks everyone for joining today. I'm going to be talking about the research I conducted for my master's degree at the University of Manitoba. And the topic was ice roughness estimation with remotely piloted aircraft, or drones as they're better known, and photogrammetry. So river ice can have really large negative consequences on water resources in northern climates. It can heavily impact the amount of hydropower that can be processed through a reservoir. It can damage structures like bridges, spanning rivers, and it can also, in the spring, be a large cause of flooding. So when the ice pieces break up during the freshet and move downstream, they can clog on constrictions and cause significant backwatering. The picture on the right here is from Selkirk, which is about an hour or so away from where I am now, which they have a pretty good experience with ice flooding every couple of years. But how does river ice form? So it all begins when the water reaches 0 degrees Celsius, and at that point, two types of ice commonly form. The first being border ice and the second being Frazzle Ice. Border ice is formed in slower moving water, and it forms at the edges of the river on the banks and slowly encroaches towards the center. So here's a picture from the Assiniboine River, close to home for me at least, and you can actually see the various lines of growth that occur as the ice expands from the outside towards the middle of the channel. And typically this expansion would happen overnight when the water is losing the most amount of heat. So the one thing to know about this ice is that it usually forms very smoothly. And that's as opposed to something like Frazzle Ice, which is formed in more turbulent water and begins as small, sticky, plate-like particles. So this is ice that's forming kind of in the water column, and then as it's being worked around by turbulence, it doesn't have a chance to form these smooth sheets on the surface, but instead is formed as small particles. After Frazzle Ice is formed, it will be transported downstream, where depending on the turbulence intensity of the water at that point, it can be forced to the bottom of the bed, where it can contact and freeze and begin to form anchor ice, which can slowly accrete through acquiring more Frazzle Ice particles or through thermal expansion. Or in areas with lower turbulence intensity, such as pools or shallow, or like, I guess, bends in the river, the Frazzle particles can float to the surface and flocculate to form ice pans. And these pans will be transported further downstream. As they go downstream, they will freeze and thicken a bit more through thermal loss. And eventually, often these pans will jam up in some sort of constriction in the river. And when they're all forced together, they can freeze together to form a competent ice cover. And as that cover expands further upstream and there's more weight of ice behind it, that cover can break and crack, forcing sections of the cover back onto itself, where it can freeze and thicken in what's known as a mechanically thickened ice jam. So ice covers formed in this way are generally much more rough than those seen formed through border ice. So ice roughness is one of the really important determining factor for the severity of flooding, and it's a really important parameter in hydraulic modeling of river covers in the winter. However, the roughness is really difficult to measure or estimate. The sort of back of the envelope bread and butter calculation for fluvial ice roughness is generally done through a relationship known as the Nezhikhovskiy relationship. So this is determined by Nezhikhovskiy in the early 60s, but it was based on a handful of observations taken on Russian rivers. And the relationship works out pretty good. It seems pretty convincing. On the bottom axis, you'll see ice thickness, and it corresponds to a thicker ice cover generally corresponds to a more rough ice cover as well. So aside from just using this sort of back of the envelope calculation, you can also back calculate the ice cover roughness using inverse modeling. So if you know the water surface elevation and flow with a decent resolution, you can determine the ice roughness that would be required to make those conditions happen. Alternatively, with more manual methods, you can go out onto the cover, drill a hole, and take velocity profiles or measure flow. Or you can even cut a chunk out of the ice, flip it over, and just using a ruler or whatever, try to figure out sort of the dominant roughness height on the underside. But all of those past two methods, they're slow. They can be really expensive to get the amount of data required, and they can be really risky for technicians. Going out on an active ice cover is really, really unsafe in a lot of ways. So what's a better way to approach this problem? If we could find a way to safely and accurately measure surface ice roughness, would it be able to tell us something about the subsurface ice roughness? So that's the essential question of the research here. And you can see this diagram kind of illustrates what the thesis, I suppose. So if you have an ice cover that's formed by sort of random stacking and refreezing of plates of ice, I think it's pretty reasonable to expect that there could be some relationship between the sort of random roughness seen on the surface and what would occur on the subsurface. But keep in mind, this would only be true for newly formed ice covers. There's various processes that happen along the winter, which will act to slowly smoothen the underside of the ice cover. But we're really mostly interested in peak roughness anyways, if we're doing estimations on risk of flooding and that kind of thing. So remotely piloted aircraft, RPAs or drones, have been widely used in topographic research. And recently they've become a lot more accessible to everyone. Basic consumer grade drones like the one that we used in our research collect 4K image stabilized video basically right out of the box. The drone that we used for this research was really nothing too fancy. I think it was under $3,000. So it's a really good tool to very quickly and very safely gather way more data than you could possibly hope to do manually. So I just want to show what's possible with this technology. So here we're recording a video from the drone hovering about 10 or 15 meters above the water surface. And we're seeing here things that really we haven't been able to see in the study of ice in rivers so far. A helicopter would be much more expensive than our research budgets usually allow, and I don't even know if they could really be flying this low on a river. Satellites, of course, are way too high up and don't have resolution high enough to be able to see these kinds of things. So for not a lot of money and really not a lot of training, we're getting brand new, much better data than we've ever had before, which is really exciting. But coupling the power of drones with the algorithm of photogrammetry, it's possible to get a pretty detailed 3D surface model of something like an ice cover. So photogrammetry uses changes in perspective and common points across multiple photos to establish distance between the camera and the points of interest. So this algorithm works in a similar way to how your eyes perceive distance through the parallax error. And as long as the points that you want to capture are found in at least 2 images, then the algorithm can use it and reproduce it. In this research, we used Agisoft PhotoScan Professional, which automates a lot of the process for us, which is really nice. Photogrammetry using drone images have been used in materials estimation, in post-construction monitoring, and it's even been used to estimate roughness, although so far only with gravel bed rivers. But how accurate is our relatively inexpensive drone and photogrammetry setup? Additionally, we have a field limitation where we have to place all of our georectification targets, which are basically just known points that we want in the field of view in our study view that we can then georectify the rest of the surface with. So ideally, those points are kind of equally spread across your study area, but because we're trying to make this whole process safer, we're only putting targets on the banks of the river and only on the left bank in our case, because that's the only bank we have road access to. So with all these limitations, we wanted to know if there was some kind of error that would be incurred, especially on the far side of the study area, which it would be 200 or more meters away from our most known georectification target. So we set up a simple test where we flew the drone over just a totally dry land scenario. It was a tree farm close to Winnipeg here. And we put out georectification targets throughout the area and then ran the photogrammetry algorithm using various subsets of those points, and then compared those results to the case where we used all of the points altogether. And we got pretty good results with about a maximum of 3 centimeter vertical error, which for us is certainly fine. That's around the resolution we would hope for something like a field GPS unit. So it's yeah, so we answered our question there. We didn't have any significant incurred error. So we have our method, we know it works well, but where are we applying it? So my field site is on the Dauphin River, which is in central Manitoba, 300 kilometers north of Winnipeg. The river flows for 25 kilometers from Lake St. Martin and into Lake Winnipeg. The last 15 kilometers of the river is really steep for Manitoba standards, at least. It's at 0.15%, which you can compare to the Red River, I think is 0.00001%, so very flat. But what's interesting is with that extra grade, we get a lot of really interesting ice processes happening. So a lot of kind of fun mechanical thickening of ice covers. This site has been monitored for the last 5 years. We've got water level loggers at all of the sites indicated with the DRLL in the map inset. We've got a fully operational weather station that runs year round. We do ice elevation survey as well as capturing aerial images. And yeah, all of this together makes the Dauphin River one of the most heavily instrumented fluvial ice monitoring sites in the world. So we have our 3D surface now, but these surfaces can be in excess of 600 million points. So they're very, very detailed. How can I take those points and find a single number that quantifies the roughness of that ice cover? So I started by taking a 50-meter subset from the center of the river. But even within a subset like that, there's some variations in the surface roughness that are not caused just by the ice roughness itself. So this is things like the slope of the river, or even as water levels decrease, you can get a bowing in the ice cover, kind of making it like a dish shape. So to kind of level that out, I applied a linear model to this 50 by 50 meter subset just to adjust the absolute elevation down to 0 and to take away the surface slope mostly. And after that process is done, I applied a 2D Fourier transform with a tunable bandpass filter to remove any of the other unwanted frequencies, which are things associated with noise in the image, as well as other large-scale impacts. So the surface data were then grouped into 3 categories for statistical analysis. The raw data was the entire original unadjusted surface. The general data was all of the adjusted surface. And then the peak data was taken as a subset of the general data, corresponding just to peaks in the ice cover. So from a roughness perspective, the peaks are generally what is dominantly causing roughness in a fluvial setting. So that's the same way if you're doing like a pebble count in a river, you're looking at the D84, or sort of the largest particles in the river are kind of dominating the roughness regime. So through literature review, 6 roughness height characterization methods were identified. So this is the inter-quartile range and standard deviation of the general data. So this is taking the DEM, I guess, the 50 by 50 meter subset, and finding the standard deviation of the height of that ice cover. As well, you can run the minimum and maximum peak value of the peak data set. You can find the average of peaks and the 84th percentile of those peaks. So all of those values become the D value in this equation on the right-hand side, which is a modified version of the Strickler equation, which in the general version relates roughness height to a Manning's roughness. And it's just modified here on the right to correspond better to ice covers. So we've got a number now, or we've got 6 numbers that represent possible ice cover roughnesses. How can we go about validating them? So since we have really good instrumentation and historical data for this river, I was able to use inverse modeling to back calculate the required ice cover roughness to give us the observed water surface elevation profiles. So I originally intended to use a HEC-RAS model to calibrate the ice roughness, but there's just a lot, like the field of fluvial ice roughness modeling is still evolving, and it's incredibly complex. And I wasn't surprised when HEC-RAS really wasn't up to the task. So instead of, it would have been, I think, an entire other master's to go about trying to have an accurate ice roughness model of this whole river. So just for these purposes, I went to a simpler model and just looked at one-dimensional attestation hydraulic modeling based on Manning's equation and the observed water surface elevation slope. And then roughness was back calculated using the Sabaneve equation, which is there on the right. It's kind of complicated, but in the end, we get a computed ice cover roughness. And when that's compared to the results that were seen through the RPA analysis, we had generally good agreements. Of course, there is a bit of scatter, but what was important to see is that generally covers that were seen to be rougher through the RPA analysis also had a higher modeled roughness. So here the 84th percentile seemed to be one of the best metrics, but the max peak value also did quite well. But again here, I don't think the max peak value is what we'd want to go with, because it could be heavily influenced by a few outliers in the set. But you can also compare these results to an even simpler model of ice cover roughness, which is the Nezhikhovskiy equation that I introduced earlier. And here we got really, I'd say really compelling results, much tighter data. Interestingly, the max peak performed very well again, but like I said, I would hesitate to say that that's the metric that should be used going forward. But again, the 84th percentile of peaks did quite well compared to everything else. So this relationship between the Nezhikhovskiy roughness and the surface roughness can also indicate a link between surface ice roughness and ice thickness, which, if you remember from the Nezhikhovskiy equation, is entirely based on ice thickness. Additionally, in evaluating the 3D surfaces produced through the RPA-photogrammetry, I found that there were 3 distinct forms of roughness that were seen on this river. So that's rough ice, smooth ice, and ridged ice. So rough ice occurred more in the turbulent sections of the river, as we might expect, and seemed to be more composed of crushed and stacked frazzle pans. Smooth ice was observed mostly in slower flowing sections of the river, so bends and pools, and was primarily composed of thermally grown border ice. And then what was really interesting to see are these ridged sections of ice. So they would often occur in smooth sections, but they would form quite large hills. You can see in the bottom graph there on the right, just a totally different order of magnitude for roughness on the surface, at least. So that's looking like around half a meter of height above the sort of general ice cover, which you can compare to sort of roughness elements in the rough cross section at the top. It was sitting somewhere around 10 centimeters of roughness. But of course, these sort of large macro structures might not be telegraphed to the bottom of the ice cover. I guess it was just more of an interesting observation that the RPA data could pick this up and give us a really accurate view of what's kind of going on. And you can also look at the statistical properties of sort of examples of these roughness regimes. So here I've got pictured rough, smooth, and ridged ice covers. We've got the picture on the bottom, and then over top of it are the corresponding distributions of roughness height values. So rough ice appeared to have the most normal-like distribution, although I will say all the distributions I tested really flamboyantly failed the a normal distribution test. So they're nowhere near actually normal according to the test. But I would say that the rough covers had the most normal distribution. Smooth covers were a lot more peaky and had a higher kurtosis value, while in the ridge data it seemed the most irregular, likely due to the roughness contributed from a ridged area on what is an otherwise smooth surface. And even in some of these samples, you'd see an almost bimodal distribution. So in conclusion, RPA photogrammetry performed well in winter fieldwork on fluvial ice covers. It can produce accurate 3D surfaces of snow and ice. The modeling approach was perhaps not suitable and did not match the observed roughness values, although the observed roughness values compared very well to the Nezhikhovskiy roughness. And the 84th percentile and mean peak of values seem to perform the best. And there may be evidence for a possible link between surface ice roughness and thickness, as seen here. So thanks everyone for tuning in. Thanks for listening. It's been great to present to everyone. So I'll take any questions now.